Hi. My name is Eitan. We're going to have it in English because I can't speak Russian and you won't understand Hebrew. So we just do it in English. I work in Wix in the Tel Aviv office. And we're going to have a little workshop today about performance. And hope you'll have fun. All right. So, why should we care at all about performance on websites? Well, I think it's kind of clear. It is critical for user experience. If something works fast, then I stay and I can wait a little bit, but if it's a bit more lagging than that, then I'm just going to go away. In addition, not only humans browse my website, SEO and search engines also browse my websites, and there's a penalty for slow sites. And besides, your competitors care about performance, so you better should too. Originally, as you know, DOM and JavaScript are not really created for big web apps. This is the first HTML page, I think, ever. It's a document, it's not an application. Yet, here we are today. This is Wix website editor, and it's a big, complex web app. So web apps, if we talk about performance, there's much stuff to talk about. It's not only like JavaScript where you can just enhance or make changes to make it run faster. Network and paints and rendering and all kind of stuff. All these things take time. So we're kind of going to talk about much of these stuff later on. So here's the agenda for today. It's going to be 4 parts. We're going to have a break between each one. So stay alive. Bear with me, kinda. So in each step, we're just going to talk about some theory, understand some rules, learn about some tools, how to find the bottlenecks, how to measure, like, where am I wasting my time. And we're going to do some little exercise. That's why I wanted you to bring your laptops. It's going to be a little competition, but we'll get to that later on. We'll focus on V8, which is the JavaScript engine which runs in Chrome and Node.js, because that's what I'm most familiar with, and it's the most documented. And I don't think you want to hear me talk about Internet Explorer, so we'll stay with that. On the way, there's going to be some links here and there on the bottom for references and more reading, so take the time later on if you want to go through that. So how would you optimize broad JavaScript? It's a language which is dynamic. It's not strong typed. Properties and methods can be added, removed. The object, you don't really know anything about an object or a function or whatever primitive that is. So basically in Chrome, in V8, there's the notion of hidden classes. Anybody heard of hidden classes? Know what it's all about? So pretty much V8 kind of assumes there's no classes in JavaScript, so it kind of creates it dynamically. For example, there's a point object, and then there's I call it twice. So when V8 runs it, kind of creates this little structure which looks like a linked list. So first, you create there's a point object, and then, all right, it has an X property, then it has a Y property. That's the first call. And then when it's called again, this structure is cached. So when I'm going to call it again with the 33 and 44, it already has it. So it runs kind of fast. It's kind of an optimization. But if, come and say, you add like an addition property later on, so that kind of makes it impossible to use the caching. So there's a new list created, and then you kind of lose the optimization you got before. So pretty much what you can take from it is that you always want to initialize properties in constructor methods because it makes sense, and you always want to do it in the same order because If I'm not going to do it in the same order, I'm going to have x, y on one time. I'm going to have y, x on another time, which is just as legal. It's the same result, but caching is a bit different, and you're not going to enjoy these optimizations in this case. So in modern JavaScript runtimes, there's just something called JIT, which is a just-in-time debugger, a compiler, sorry. And modern JavaScript is really compiled to machine language, unlike, for example, .NET, which there's an MSIO, this intermediate language before the machine code that runs. And V8's got actually two different compilers. One is called the full compilers. That's really its name. And this compiler gets a JavaScript code, and it can run anything it gets. So anything which is legal in JavaScript, every feature that JavaScript has, the full compiler knows how to run. And you want to run it as fast as you can, because the more time you waste on this compilation, then that's time that the browser is busy doing this compilation and not doing anything else, for example, rendering or whatever, or being responsive. And there's another type of compiler, which is called the optimizing compiler, which produces really great code, but it takes longer to compile. So this compiler doesn't run first, it runs on the way. I'm going to explain what I'm talking about. So the full compiler can process, as I said, any JavaScript code. It runs really fast, and it starts executing as soon as possible. It generates good, but not great code. It creates something that's called inline caches. Inline caches is kind of when you call a function and you pass it parameters. Let's say you pass 2 integers. So it kind of marks there, hey, this function was called like this and this amount of times, and I got 2 integers as parameters. So later on, you can assume it kind of has some knowledge about this function. It knows that this is a function that's called this and this amount of time, and that it gets integers as parameters, which is very important information in order to compile it efficiently. So each time the function is run, it kind of validates with the assumptions that it made, and there's optimization it makes. Later on, this optimizing compiler runs hot functions, which are called a lot of times. And then sometimes it kind of puts the functions in place in order to shorten, to make it faster. And it uses that information that was collected with these inline caches to know that this is a function, although there's no types in JavaScript, but it kind of has that information now. This is a function that is called with integers or with strings, then it can optimize it on that matter. It's slower, but runs later on. But the most important thing is that it cannot process some language features. Some things that are legal in JavaScript can't be optimized with this compiler. Now, it's important to say that this is how it is today. And tomorrow, the guys in the VA team may introduce some new features or some new options that are possible. So we kind of need to measure each time to see and then understand and learn something from it. This is speculative, so it's super legit that I'm going to call the same function this one time with integers, and the other time I can call it with strings, but I may lose that optimization that I have from before. So in that case, de-optimization occurs, and that takes time as well. So it's a double, it's bad 2 times. And one time it's bad because it's not optimized, and the other time it's bad because it was optimized and then de-optimized, and we're wasting the time. So here's pretty much a short list of bailouts. These are things that are currently not supported by this optimizing compiler. Now I want to show you an example. I have some, kind of bear with me. I promise you're going to see everything. Is that better now? Yeah, even too big. So there's a main.js function here. Can anybody see? Yeah? All right. So there's a compute function here, which kind of logs. I'm starting, takes the time from this line until it's done, until time end. And it runs lots of times a save function and then a save function. Now these two functions are right here, right above here. As you can see, they do the exact same thing. Only that one is wrapped in a try-catch expression and one writes it straight away. So we're gonna kind of run these 2 times and see how it performs. Function that runs this and this amount of time is considered to be hot function, so we should expect that it will be optimized. So I'm just going to run the save function. I'm going to click start. Wait, I'll make my console here. So it took 4 seconds and 229 milliseconds, which is, I guess it's legit. Now let's try to see. Let's run the unsafe function only, without the save function. That takes 99 milliseconds. So we want that optimization. We want to make it happen because, as you can see, it does have a big impact. From 4 seconds to 99 milliseconds is a big difference. So we kind of talked before about monomorphic and polymorphic functions without kind of saying. So this add function gets 1 and 2. So far it's monomorphic, but it's very legal to call it again, and I'll get the AB concatenated string, but I'm going to lose the optimization in that case, so you kind of want to avoid that. One more thing, anonymous functions are not optimized, so you should want to do the same thing, but just call it with a named function to get the optimization happening. Another thing is the scope. This result parameters is from a different scope. We have 2 scopes here, actually. There's one scope which is going to be the global scope for now, and there's a scope for the function itself. But now, the way scope resolving works, it's kind of the doStuff function looks at the result and say, all right, is it defined here? No. If it's defined here, well, it's good. If not, goes to the other context, finds it there. If not, it's going to go the whole chain till it gets to the global scope, and that takes time. This hopping takes time, so you may want to add, you want to cache it. So just before the for statement, you want to say var local result equals result, and kind of use the local result, so it's not going to resolve the scope each time the loop runs. A word about arrays. There's 2 types of arrays. Fast elements, which is kind of like an array in C++, for example. It's linear storage, and it has sequential keys, and it starts with 0. And this is a fast and efficient access. If you want to run through the whole array, you want it to be optimized to a fast elements array. But as you know, you can use an array as actually as a hash table. Like actually arrays are like stored as objects, even in JavaScript. And in that case, it doesn't get optimized, and it's actually is saved as a hash table. Arrays which are sparse, so there's like holes inside, are not being optimized to a fast elements type of array, and it takes more time to run at runtime. So if you want to get your array optimized to be a fast elements array, you don't want to make holes. So if I just put something on the 3rd location, then on the 1st and the 2nd there's nothing, that's the hole, then it's not being optimized. You want to use the push method in order to get that happen. You don't want to mix stuff. If the array kind of have to have the same data type inside, so either it's an array of integers or arrays of strings. Otherwise, it has to do some boxing in memory because to manage the different types. And this is kind of like something that gets unnoticed. If you access an array, you know, sometimes we check somewhere if that's defined or not defined. We say, hey, it's undefined. All right, I know it's not there. But just by accessing that place which is not defined, you kind of ruin the fast elements optimization. So You don't want to access your array on indexes which is not defined. And again, don't make holes because it kind of de-optimizes it. This is a bit out of topic, but I thought put a slide here anyways. When we measure, I showed before, when we measured, we used the console time and console time end to measure how much time it took me to measure what I ran. But sometimes you do deal with animations, or you deal with things you need to be more precise. Sometimes measure by the millisecond is not enough. You have something that runs 30,000 times and runs for 10 seconds. Sometimes you need it more precise. So HTML5 has a new API called window performance, high resolution time, and you kind of get fraction of milliseconds in measuring. We're not going to deal with that today, but just so you know, it is supported. It's not available on Safari, but there's a nice polyfill you can use, so you can use it if you need. I kind of put the HTML5 rocks here link down here, so you can browse that if you want later on. All right, so console count. If you can use console count in order to see how many iterations, you put console count in your function, you see how many iterations you get it like printed out each time you pass there. You can use the CPU profiler in the DevTools. I'm going to show it in a minute. And you can actually run the V8 compiler with these command line flags. So trace opt will show you what's being optimized and what was optimized and then was de-optimized because something happened. And you can have a list of bailouts, like stuff that wasn't optimized because it's not, it can't be optimized at the moment. So, based on that, I want to have a little session together. So we're going to have a little competition. So here's a zip file. I kind of put it on that URL. You can see it here. So just go ahead and download that on your free time. There's a little code that what it does, it finds out the 15,000 prime number. It's always going to be the same number, but it's not that efficient, and you can kind of improve the way it runs. So let's take about 15 minutes and try to make that run a bit faster. I'm going to put a link to the slide if you want. So if you want to take a look at the what we talked about, and good luck. I have prizes, so. So if you look at the index HTML file, just kind of question everybody had. So this is actually where the work is done in the get prime function. So if you use console time just before, and then console time end with the same label, you're going to see in the console how much time it took to execute from that moment to that moment. Now, as you improve the way it's written, you're going to see, hopefully, you're going to see the time gets faster. But this is one easy way to see how you did. All right, we're going to move on. 1.7 seconds is the best, I think, here. I can show you my solution. Well, first, congratulations. I got mine to run in 11 milliseconds. I can show you. So let's take a look at the original. Pretty much, it's all the same. These are all the same tricks. This try and catch is pretty much useless. You don't need it. You can remove it. I don't know if you noticed this for loop. This equal sign makes you iterate on a non-existing item in the array, so it kind of de-optimizes the fast elements array. So you don't really need that because it doesn't exist, which Here, for example, you don't need to divide. You don't need to. You can just make sure that I is not that this is not 0 to begin with, and then you just don't need this throw new error, and then it can be optimized, and a bunch of other stuff. But the main thing here is this algorithm to find the prime number. Kind of sucks. It runs on all the numbers until the number and checks if they're divisible. And you kind of have to run until the square root, to find if something divides by another number. So you can save a lot of time here because the algorithm sucks, which is one of the biggest points here is that usually what you want to optimize is what you actually execute, because usually that kind of sucks even before the optimization in JavaScript. So that's one thing we can say. That's usually the code we run by itself is could be written better. All right. So DOM stuff. Everybody know what DOM is? I hope so. So from the server to the screen, there's a bunch of stuff that's going on. What you do, there's like lots of HTML, download lots of tags. You get user agent, default, style sheets. This is built into a DOM tree. The browser takes all these styles and makes a style structure, creates something that's called a render tree. Then user, for example, zooming and stuff like that takes into account. And then eventually everything is painted on the screen. One thing that happens once it's painted, if things are changed later on, for example, I change a color or add CSS, stuff like that, then I need to repaint that. Painting, as you know, we have one thread. Painting takes time, so that's time the browser is busy painting instead of doing other stuff. So we're going to see how to measure that and how to improve that. Adding or removing or manipulating the DOM pretty much changed the way the document looks, the way changes what we see on the screen, so that causes reflow and repaint. Let's take a look here for an example real quick. I have like an example here that has I changed these CSS properties. Margin, background, transform. One thing we want to see on the timeline here, don't need this, too big. All right, and we're going to record that, and once I change the background, you see that a paint and a composite event were called. So each time that I do this, if I change the background to green or add margins, you can see that these events in the events timeline here, you can see that it causes repainting and compositing from the beginning. Resizing the window, changing the font style, scrolling, all these change what we see on the screen at the moment. They cause repainting. So what you can do, wait, sorry, too small. Yeah. So what you can do, for example, once you change each style, each one of these causes repainting. So if you have a bunch of changes, you want to make it in one change. For example, use a class, and then it causes one repaint with all the changes. So you can save time on that. If it's a heavy modification, you can hide the DOM, hide the specific element, change whatever you want, and then display it again. That saves the painting on each step on the way, because you don't really need these steps. You want it on one step. Sometimes you can clone and then replace. This is a bit heavier, but depends on what you do. It may be applicable. For example, here I access the DOM 10 times, adding 10 elements. What I want to do is really don't want to do that. I can create a document laundry time. I can create a document fragment, which kind of aggregates all my changes to the DOM, and then append it. The advantage in the document fragment, comparing to just an element, is that it's a virtual element. You don't have a div with the stuff inside, then you have to get rid of the containing div, for example. You can just add a bunch of nodes. It doesn't have any effect on the structure itself. Accessing computed styles like Windows scroll is a bit expensive, so you want to cache that and then access it from the cached version. So all in all, these APIs, one of them is DOM, but other APIs as well, they take time to access. So if you can, don't access them, but you can't really do a lot of stuff without accessing DOM. So try to optimize the number of times you access the DOM. For example, this is a jQuery syntax. I don't have to select the item 3 times. I can select it once. I can cache it, and then perform my changes, and it will be done in one access to the DOM. Let's say I want to add event listeners. This does add 3 listeners because there's 3 images. You can do it with 1 listener. It's more efficient. If you listen on the container itself, and then you just add. You can just call it with the clicked image. All right, so we saw the timeline events. I'm going to show one tool you can use. Here's just a page with some divs. So there's a continuous page repainting little tool. You can turn it on here in the options. Can't zoom that, so we can't see, but there's a little black box there that says, if I'm going to paint this page, it's going to take 11.9 milliseconds at the moment. If I'm going to remove some stuff here, so I can see that now it's going to take just 4 milliseconds. So when you have a page and you want to know how much time it's going to paint it, this is one thing you can turn on and kind of follow with that. All right. So I have another task for you, if you're up for it. Surprisingly, the link is similar. What I'm going to show you is going to be 2.zip this time. I'm going to show you what this is about. We have some sort of a timeline with some posts, which we'll show eventually. So there's some timeline with bullets here on the way, with comments and posts and whatnot. And it takes a while to show, as you saw. And we want to try to improve that, so good luck on that. Let's take about 15 minutes for this task. Maybe some of you missed this before. This little Google Doc is available on this URL. So what we're looking at is this tiny URL. So if you want to open out on your machine, so go for it. There's one thing worth mentioning that I kind of forgot to show you. If you refresh, you open the timeline tab on the events, you can see that during the time it takes to load, you can measure, like, over here you can see that this little load time, I'm spending here almost 8.5 seconds only on rendering. So this is what you want to measure. All right? All right? All right. So you did a great job, actually. Someone here got it on 600 milliseconds, which is the best in the room. pretty much refactoring the CSS outside and kind of not accessing the DOM unless you really need to. That's pretty straightforward. I think there's a break now for lunch. So enjoy, and we'll be back here. We're going to start exactly at 10 minutes before 2. So I'll see you soon, and enjoy your lunch. Yeah, can you hear me? Did everybody have lunch? All right. So welcome back. Thanks for coming back. So continue to the next session. We're going to talk about animations. I feel like Madonna with this thing. All right, so when you talk about animations, and so pretty much we're talking about how many frames per second we're rendering. Most screens, the default refresh rate is 60 Hertz. And so 60 frames per second is leads to smooth animations, which means that if in 1 second you have 60 frames, you have 16.66 milliseconds per frame. You don't need to animate at a higher frequency because there's no use. And in each frame, browser has to do all the following work in order to render smoothly. Let's just understand a minute. This is a 15 frame per second animation. This is a 30 frames per second animation. This is a 60 frames per second. So you see this one, the one on the right is smooth, and the one on the left is kind of choppy and annoying. And so you want to be in a. We're trying to make our applications animate like this, so it would be smooth and cool. So in order to understand how this works and kind of tricks, you need say a couple of words about CPU and GPU. So CPU, I guess most people you know what a CPU is. All the calculations that are done on a computer pretty much are executed there. The GPU is a graphic processing unit, which is on the graphics card, and that's responsible for rendering graphics. It's actually specifically designed for that. So complex math stuff and geometrical calculations are done on the graphics card. So if you take such stuff, such calculations, and put it on the graphics card to work, we can get performance gain, significant one. The way GPU works, there's a layering model. So the browser renders a page. It takes polygons or elements that are rendered, and it moves it to its own layer, and it renders independently on the GPU. And later on, it's composed and drawn into the screen. What we gain from this is that we don't have to repaint the whole page again after that was done. Only the change is rendered. Here's like an example for layers. You can see that each one of these, it's just an example for transformation. Each one of these CSS properties is optimized to run on a GPU, and it does it pretty efficiently. In addition, specifically opacity is something that GPU does very well. So the browser kind of automatically does that for you. So what can we play with? Layers are automatically created by the browser for some specific stuff. Video element, any kind of flash or Silverlight, canvas element. The 3D CSS properties and the CSS filters also get their own layer. And each time you animate opacity or transformation, you can get it gets a layer. But you can force a new layer by kind of adding a transform, translate or transform. This actually has no impact, but that does make it a 3D CSS, and you force the browser to create a new layer for that. I'll show you an example. So here's a very complex page with a div. Sorry. So you see anything? So this is just a box, and I'm going to show the layer borders. So what you can see, besides the little grid, you see, it's hard to see, but you see kind of an orange rectangle which circles the whole window. Do you see it? I'll turn it on and off so you can see. You see there's an orange thing? So this is a layer which is created for the whole page at the moment. I can go on that div and add And if you can see now, there's a new layer created on the box. So that now that box has its own layer. So we kind of threw it now to the GPU. The thing is, don't overuse that. These layers take memory, and it's not always the right thing to do. So only if that actually improves the performance, you want to do that. Otherwise, spare that. Animations are not only in JavaScript. Well, you can do animations in CSS and in JavaScript. The good thing about JavaScript animation, it gives you full control. You do, you know exactly what runs and when, and you can kind of control that. CSS animation is optimized by the browser, but it's hard to combine a few animations. For example, I use like an animation with keyframes, so you kind of give instructions what to do and when. But you have multiple of these, so it gets a bit harder to maintain. So what we want to do, for example, well, if you want to do frames in 60 milliseconds, this is not the best way to do it, because you kind of have excessive calls to animate. What you do is you want to request animation frame. And what a request animation frame does, it kind of gives you kind of tell the browser, hey, I'm animating stuff here, so kind of take care of that for me. So don't animate if it's not visible, or don't animate if it's not necessary, or we're under the 60 frames per second. Here's like an example page. It does the same thing. The left part is using set timeout, and the right part is using request animation frame. So here's the callback efficiency. Of course, it's 100% because it's request animation frame. But here, the callback, if I call it each 10 milliseconds, then only 59% of these are needed. So all the other ones are excessive. And it kind of runs my battery. If I do it every 1 millisecond, it even gets worse, and it drains out. All right, so tell the browser you're animating. It allows it to synchronize multiple paints. We saw before about paints. It gives better performance. If it's invisible at the moment because you're in a different page or you scroll down, then it doesn't animate and it saves battery. So this is something that mostly pages with parallax do a lot, which kind of do animation on the scroll. But what you want to do is kind of cache. When there's a scroll, you want to see, okay, I'm going to cache the scroll at the moment, and then I'm going to animate on the last scroll Y at the moment. That's what it's called. So it doesn't really matter. You get a lot of values for the scrolling position on the way, but they're not needed. They not actually needed in order to animate. Only the values which each 16 milliseconds are the ones that are really necessary for the animation. So the translate Z hack, it's called the Null Transform hack. It's been used for a while now to promote elements in their own layers, as we saw before. It kind of forces a new 3D layer. That's what we can do at the moment in order to play around and put stuff on the GPU kind of force it into the GPU, but it does take some RAM, and you have to make sure it really helps performance, because if you force a new GPU layer and you don't animate eventually, that could happen, then it's a waste. And that's set up, and then you move it to the GPU, it takes time. So you kind of always have to make sure that that does help your performance. So what you really want to do is kind of say to the browser, hey, this element is going to animate sometime in the future, it's going to change, so kind of know that when you render it, so get ready for that. So there's a new CSS property exactly for that. It's fresh new. The editor draft in the spec is from a week ago. And that kind of informs the browser ahead of time what's going to be changed on that element. And it gives him you leave the browser the way, the power to decide what kind of optimization he wants to do on that element, if at all. And potentially expensive work to prepare that operation is done before it actually happens. And it's very simple. You just put CSS on the element and say, I will change transform, for example. So it knows to optimize it accordingly. You can specify multiple properties. And the trick here you want to do is you want to set the will change property just before that happens, not too early. For example, if you want something to animate on a click, you can set the will change on the hover, because you're probably going to hover before the click. So you can add it. You can add that CSS by using JavaScript at that time. It has an intention to ship, so it will happen. It is supported in Chrome, in Canary, in Firefox nightly as well. It says under consideration in Internet Explorer, whatever that means. Opera, it's supported in the next version, and couldn't find documentation for that for Safari. So this is a fresh thing that will kind of avoid these hacks that we just talked about, but so far we're staying with the hacks until this is out. I want to show some tools about measuring animations. So here's a little page with a nice fisheye. I'm going to open the DevTools here, go to Timeline. I'm going to click Record. And you see there's a little bar here. So when I scroll, you see there's a line that says 60 frames per second on the right here and 30 frames per second. So you kind of want everything to be below the 60 frames per second. That tells you that this is efficient enough. If I do it a bit faster, you see it's more than 60 frames per second. That kind of depends on the browser too. Refresh that. So that's that. Paint rectangles. You can turn on the paint rectangles, and now you can kind of see, you see that the green flash, it says, hey, this is now repainted, right? So this whole thing here is repainted. You see when I change the window, that's also repainting the whole screen. So this is another tool you can use in order to see what's painted and what's not. And of course, the layer borders that we see, which are now shown on the whole screen. It's kind of hard to see. So, surprise. I can't hear you, sorry. If the will change, if you don't use Canary, then the will change doesn't exist yet. You need the Chrome Canary version.
But if we have will change, should we describe the will change properties?
Yes, you should. And then
That we change with transition.
yes, you should say we will change. The transition is done with transform. So you should say you should say which CSS property you're going to animate. So if it's say the animation is on the opacity and the color, so you say we'll change opacity and color.
If we change opacity and color in transition, we also include it in will change.
Yes. All right. All right. So surprise, this fisheye thing we saw just now, it's number 3. So we're going to try to improve the performance of that with the layers pretty much. And good luck. We're going to take 15 minutes for that. If you turn off the show paint rectangles, you can show the frames per second meter. It's the little black thing on the right. So unoptimized, I have like 9.5 frames per second at the moment, or 20 or whatever. So you can measure with this little black box the frames per second meter. So last part, I'm going to talk a bit about garbage collection and memory management in general. So pretty much manual memory management is like on manual memory management, you as a programmer have to take care of the memory. You have to free, once you allocate, you have to free it later on. And sometimes it's kind of easy to forget stuff, and then eventually you have memory leaks, and then the whole operation system kind of kills your app. On automatic memory management, so whenever something is not used, then it's reclaimed automatically. For example, we have you have the document, you have the root, which points to this object, which points to that object, but here in the middle, there's an orphan chain which cannot be accessed in any way from the root, hence it's garbage and it will be collected. So the GC kind of finds these and frees them. Each time, this is the timeline which shows the memory state, and each time there's a garbage collection, you kind of see the drop, because this bar shows how much memory is taken. Once it's dropped, it means there's memory free. These interruptions are considered expensive, and you want to avoid them as much as you can. And pretty much the only way to avoid them is not using memory, which is kind of hard. So what we want to do is use as less as we can. So you can kind of have an object pool concept. This is not native JavaScript. This is something you have to implement. But you have an object pool. You get an object. You kind of do your work with it, and once you're done with it, you return it to the pool instead of just abandoning it, and then reuse it again whenever you need it next from the pool. And then you see the bar is less of, here you see the zigzag, and the bar here is more calm. It happens less frequently. So these garbage collection pauses, whenever that happens, everything else doesn't happen because we're still on the same thread. And it's kind of unpredictable from a developer point of view. It's unpredictable. You don't know, the browser decides about it by himself. So you're going to want to avoid object creation and reuse the stuff you're inside your loops. I kind of want to recommend this checklist down here below. This is a nice checklist of things you want to take a look, which covers a lot of the stuff we talked about today. So check that out when you get a chance. Let's take a look at some tools we can measure. Here's a page which does absolutely nothing but waste memory. So we're going to take a look at the memory here. And as you can see, it kind of freaks out here. What happens here is that there's this a little script, I think, which kind of creates garbage and doesn't do anything. So, yeah, that too. You can take heap snapshots. I'm going to show you how to do that to inspect what's going on in your code. Stop that. In profiles, you can take heap snapshot, for example. Now this is what's currently in memory. You see all these XX strings are in memory, and that's the garbage. That was easy. Here's a little Rambo lady, which kind of wastes memory. So look at the timeline here. So unexpectedly, that's going to be on 4.zip. Let me check that. So good luck. Pretty much what we try, there's not much to do here. It's just eliminate the creation of new objects during that time it runs. So good luck. I'm just going to stare at that a couple of more times. Yeah. Hi. So between each garbage collection, between one garbage collection and another, you kind of want it to be as long as you can, if at all. So there's a solution here that I'm going to show you in a minute. This is 11 seconds between one GC collection, one GC and another one. So just so we know how we're going to measure it. All right. So we want to wrap it up. These guys here got it in 6 seconds between garbage collection. So congratulations.
Thank you.
Yep. So I want to wrap it up. A few more minutes of your time. So we've discussed about performance. We discussed how we can improve it, and what tools we can identify the bottlenecks and see what takes time and what takes memory and whatnot. I think the most important thing you can take out of this session is do not optimize your code or start writing hacks and stuff like that until you have a problem of performance. Because you can write all kinds of nasty stuff in JavaScript, but then if someone else has to read it, poor him. So try to write, once you have an application and it's working and it's doing exactly what it should, and if you have some performance problem, try to identify that and by measuring, and then see how you can improve the bottlenecks. This is a bunch of resources. I urge you to take a look at them. Thanks a lot for being here.